Yeah, so this is sort of like one of those days when you just feel guilty about the whole day. So today was the first test match in BGT, and I spent the entire day watching the match. It was an office day as well, so I did some work in the office and I spent the remaining time just watching the game. And I had to do some coding. So, for context, my first round of Google is cleared. So, the preparation that I did for first round paid off in some form or the other. I mean, in the end, you just have to go out there and try to solve the problem as much as you can, try to be communicative and try to solve the problem. That's all you can do. But that is cleared. So, remaining rounds have been scheduled, and given that it is Google, people would usually go over and beyond for this for its preparation, but for some reason I'm still not feeling it. Maybe before the weekend of those rounds I would actually go in hard and solve some more problems in a more rigorous fashion, but the underlying concept remains the same. I have solved a decent number of problems with a decent number of concepts, and in the end you are supposed to communicate your ideas. It's as simple as that. But um, having said that, there is a very good chance that you will not be able to crack a certain question, so it's never a bad idea to keep on practicing. So I'll start off with a couple of problems. So there was another problem as well that I recently submitted. I'll open that. So I have already submitted those problems. I'll just start with a basic analysis of both of those problems. Yeah, count on guarded cells. This was one problem. You can go to the problem statement of that, and then this is this problem. So one hard and one medium problem. I wasn't able to solve any of these problems. I had to go through the solution and then come back. But regardless, both of these questions were actually good, and actually they both required some sort of observation. So in this particular problem, so the first conundrum, or you can say a mental fight that will come to your mind is, should I even be using yeah, so I have made some notes here and highlight some additional notes here as well. So the first thing that will come to anyone's mind is, should I even be creating an additional matrix of size m by n? It's very easy to see that if we do so, our lives will be much simpler. But so my camera is here and I'm coding on a big screen. There is a discrepancy. So it's much easy, like it's easy to see that once you declare an additional storage space, it's much easier to process the problem that has been given to you, but at the same time, it costs you extra space. But having said that, it's also easy to understand that if you don't use the extra space, ultimately you will have to use a hash map or something to mark seen or unseen. So even if let's say I don't use some additional space, I'll still have to go through all the cards, I'll still have to move through all the cells, I'll still have to somehow remember if I have seen them or not, and all of that. So I'll have to use some kind of a data structure, and more importantly, for a cell on which I am present currently, whether or not it's one of the guards or one of the walls. For that, either I can like um, binary search on the given array. So what has been given to us is just vectors. So either you can sort and do binary search, or you can store them in hash sets. So that is again additional space, right? So if you do binary search, your time complexity can be of the order n into m log times of guards or log times of walls. The reason being that, in asymptotic case, you will have to iterate through all the elements in your cell, and more importantly, you will have to search you will have to do a binary search in the given array, that is in these two vectors that have been provided to us, guards and walls. If you don't want to do that, you can store guards and walls in, let's say, something like hash maps, and then your search won't be logarithmic. So logarithmic component will still go away, but still asymptotically speaking, you still might have to go through all the cells present in the matrix. But again, if you use a hash map, time complexity necessarily doesn't have to be of one. The reason being, there could be collisions which can blow out your time complexity to even more proportions than logarithmic complexity. So one of the reasons why people usually don't choose to use hash maps. Uh, and one more thing would happen if we use hash maps is the whole point of reducing space is also kind of compromised because you are again using space anyways, additional space. So all of these complicatedness can be avoided if you just simply use uh, an additional storage space of big of n into m, because in that case we can exactly tell what the time complexity would be. So we don't have to create a hash map and then hope there is no collisions and all of that. You can simply create an additional storage space of the matrix size and then store walls and uh, guards separately and then just go through the simulation. That would simplify the process quite a lot, and you can actually find the time and space complexity quite specifically. Space complexity is very clear, it's big of m into n, which is the size of the matrix. Um, the time complexity is bit of a headache, but it can be seen that, like, worst case, what will we do? We will do four passes. So one pass will be for horizontal pass. So for you move horizontally only. So for every card you move just in horizontal direction and cover as much as possible. If you see a wall, you stop. If you see your guard, that is not one of the marked cells, but you keep on moving. Same you do for horizontal left to right and horizontal right to left. Similarly from vertical top to down and vertical down to top. Those four motions if you do, it's easy to see that there won't be any repetitions. There will be each cell will be repeated four times, but for sure you will cover everything. For sure you will cover all the coverage that is there to offer, because we have four directions and we are exhausting them. So for sure you will cover everything there is to cover, and the complexity will be bigger four times of m into n, which is just the order of m into n. So that seems like a good solution, but again implementation is difficult. And there comes the grand idea, which is that don't do anything. Literally just go through the simulation. You don't have to do four passes. Just iterate over the entire matrix. Whenever you see a guard, you move in four directions, as long as you don't see a wall or you don't see a guard. How that would work is that, so for a particular wall, let's say, so let me do some rough over here. So this is count unguarded cells in the grid. Count in the grid. So what will happen is, let's say I have some cell I comma j here. Let's see something here. So there can be one guard here, one guard here. This is to its right. One guard here, another guard. I can say something like here, maybe. Can I bring it back? Yeah. And let's talk about what happens at the top. So let's say one guard is here. Give a space. It doesn't matter actually. And let's say one guard is here, and let's give some space, and let's say another guard is here. Now the important thing to observe is, interestingly, just G is, it almost looks like, well, I'm trying to say Google or something. But anyways, so the point that I'm really trying to make here is that for this cell, the question now is that if if I were to just do a simple simulation, that is iterate of the matrix, you see a guard and you move in four directions, as long as you don't see a wall or you don't see a guard. So the observation here is, let me just put a wall here just for reference purpose, like to see exactly what would happen in the simulation. The key observation to make here is that even in that case, at most a cell will be visited four times. Remember, in the first algorithm, if we by default make four passes, we are sure that the solution is correct. We are sure that we are under time constraints. So that is the same solution to go for, although the implementation is hard. But in this solution, it is relatively easier to implement because you iterate over the matrix, you see a guard which has not been processed, that's a different thing. You have to maintain states of the guards as well. And here is where having a matrix is like lifesaver. You can just change the states of that matrix and be done with it. Makes implementation much more easy. So once you see an unprocessed card, you can just move in four directions. And I'm saying my claim is that every cell will be seen at most four times. The reason being that, let's observe this particular cell when it can be seen. So let's say you encounter this guard first. When you move in the right direction to this guard, the moment you encounter this particular guard, you will of course not continue the right movement of this particular guard. So this is the first guard, right? We will stop the rightward movement of this particular guard the moment you encounter this guard, right? So as long as we are encountering something to the right, which is not a wall or a guard, we will continue and we'll keep on marking it seen or something, because we have to mark it something, because otherwise how will you know that it has been covered, like a guard can see it. So that's the purpose. But this guard will have scope till here, right? Similarly, this particular guard will have scope till here. It will just see a wall and return. Similarly, this particular guard will have scope till here. So basically what I'm trying to say is, it won't be the case like each of your guard are moving through the entire row span and column span. In fact, if you sum the entire space that can be covered by all the guards, that will basically be a summation of everything. Why? Because let's say this guard has now been processed. What will happen with this particular guard? This particular guard will see till its left, so these particular cells will be repeated twice, and it will see till its right. So this particular guard to its right it will cover this much. This particular guard to its left it will cover this much. Just to Control C, something happened. So I'm saying that this particular guard will cover this much to the left. Similarly, this guard will cover C at its bottom, and this guard will cover C at its top. So this particular cell will be seen at most 4 times, because any guard which is not the closest to the cell in any direction, be it right or left or down or up, it won't have access to the cell. In other words, every cell will be repeated at most 4 times. So here also you can see this particular guard will cover this much to its right, and these cells will also be seen by this guard on its left. Similarly, if there was some guard, let's say something somewhere here, let me bring that up back a bit. The alignment is getting screwed. I guess that's okay. So if there is a guard here, again that guard would also see this cell, but this cell won't be seen a fourth time if there is no guard present in this column below it. So the advantage here is that, I mean, there could be a guard, but there has to be a wall above. So for example, if there is a guard here, there could be a wall just above it and we would be safe. The reason being that we see a wall and we know that, I mean, there is nothing which is screwed up. Right? Control Z, dude. Right? So in this case also, this cell will also be seen 3 times. So it's very important to make this clever observation, and I think it's quite difficult to make this observation in an interview scenario. To be honest, this is a medium rated problem, but if like someone is expected to get to this chain of thought during an interview without having seen the problem, I would say it's very difficult to do so. So one should ideally have solved this problem before to actually think in this kind of in this mode of reasoning. I would say, I mean, it's easy to make the first observations that we need to use some additional space, otherwise we're going to run into a lot of issues, and then it's still easier to see that there we would require 4 passes to be done just to be sure. But observing that each cell is at most seen 4 times, even if you just do a direct simulation, move till you see a wall or guard, uh, and still we have at most a cell being seen 4 times, which is even better than the safe for implementation. That is a relatively tougher thing to say. So this would be the explanation for this problem, and time and space complexity both would be of the order m into n. In fact, there is a very good chance that time complexity will be lesser than 4 times m into n, because 4 is like the worst case scenario in this case. That would be that problem. This was a very good problem, I would say. In DP, again, I was not able to solve it. I watched a solution video, and then once I was like, I don't know, into 4 or 5 minutes into the solution video, it cracked. So that's one of the good strategies to solve a problem. If you're not able to solve a problem, you try to first of all, of course, this is assuming that you have given it all your energy, all that you could have done to try and solve the problem. But even then, if you are not able to solve a problem, you start watching the solution. But if something hits, then you need to stop the video or stop reading the editorial and try the solution yourself, right? Because it's still better to like trigger your like use your thinking, your brain to solve a problem rather than just, I mean, uh, relying on some external help. External help is required in situations for sure, but it's a good idea to try and solve problems by yourself. It never hurts. This is a really good problem. Because see, the first thing is anyone, literally anyone. Why is it looking like this? Let me refresh it. Something happened or what? Oh no, I think these are two separate examples. Oh, they have shown two ways. Okay. So it's very easy to see that we'll have to do DP of some sort. And for each cell, let's say I comma j. So this is actually the complete explanation. By the way, this can be like an editorial, to be honest. So it's easy to see that for any cell I comma j, you can store whether or not a valid sequence is possible till I comma j. And basically you want to return dp of n minus 1 m minus 1, where m is the number of rows and n is the number of columns. But the problem is, in order to tell whether or not a valid sequence is possible at n minus 1 m minus 1, you need to check all possible strings till n minus 1 m minus 1 or till ij, let's say. Now, till ij, what is the length? So, I rows, j columns, I plus j, and 1 is common. So, the displacement will be I plus j minus 1. Now, here is the trickier part. At I comma j, how many ways can you get a string? See, there are I plus j minus 1 characters. Each character can be either an opening bracket or a closing bracket. So, there are two possibilities at each position. So basically, you have 2 into 2 into 2, 2 to the power I plus j minus 1 possibilities at I comma j. So the time complexity for n and m would be something like n into m, because of course you have to maintain for each row and each column what will happen. And on top of it, at n comma m, you have n plus m minus 1 length of the entire string. Hence, the number of possibilities is 2 to the power n plus m minus 1. That's just insane. That's exponential complexity. However, one wise observation will save you from all that pain. The observation being that we don't really need to track the entire string. Let's just track the differences between the opening and the closing braces. Because the wisest thing to do is, if I mean, what can you do? The simplest thing that you can do is, when will there be an imbalance? Is the first question that you need to answer. So, imbalance will happen whenever you have more number of closing brackets than opening brackets. That is the only case of imbalance. So, for example, again elaborating a little bit more on this. So, this problem is, just copy this, check if there is a valid parallel. So, I know I have solved this problem before, and it's probably just better to go ahead and solve some more problems rather than just thinking about this problem repeatedly. But I still am a strong believer in the idea that you need to like completely milk out a problem, completely milk out a problem. All there is to it. So all reasoning, all thoughts, how to think, chain of thought, and what is the analysis of complexities, what other solutions could be possible. Because only then have you completely solved the problem. Like problem solving has some value in only those situations. Now, coming to an example, it's one needs to observe that. So the only case, so let's say I have an opening bracket. If this is what I give, this is balanced. Again, I have opening bracket. Again, I have opening bracket. I have a closing bracket. Is this balanced? No. But I can't say that it will always be imbalanced, because give another closing bracket and this is balanced. So the observation that one needs to make is the moment you have more number of closing brackets than opening bracket is when you are actually in trouble. Because let's say I keep on giving opening brackets, I'm still not in trouble. Let's say this is the number of closing brackets I gave, and I again gave some opening brackets. I'm still not in trouble because so this section somewhere along here is balanced, right? And then if I again give some closing brackets here, this part will be balanced. So let's say this is balanced and this is balanced, right? And once those two sub chunks are balanced, that's why balance parenthesis is like a classic stack problem. Once those are balanced, external parenthesis will also be balanced. So this will correspond to whatever is left from here, right? I'm not sure what exactly I'm giving, but that's the idea. So if you have more number of opening brackets than closing, you can never say that, you can never be sure that whether or not it's a correct orientation or not. That's the whole point that I'm trying to drive home here. Now, when will we be sure is when, let's say, you have some opening, you have some closing, you have some opening, and you have double closing. This will never be balanced because this portion is balanced, let's say, and this is the additional one. How are you going to balance a closing bracket? Hence comes our idea. Instead of tracing the entire string, which could be exponential, the number of ways to build that string is exponential, just track differences between the number of opening brackets and the closing brackets. If that difference is zero, you are already at a balanced string. And by the way, how not to run into edge cases is make sure that you are never taking negative cases. What I mean by that, let's say I have this as the first two. So difference between opening and closing will be what? -1 first, and then it will be -2. Now the trick is the moment you see anything negative, you break, because no matter what happens, it will never be balanced. But if someone just does it stupidly, something like this, right? Gone, gone, screwed up, because so he will see -1, then -2, then -2 plus 1, so it is -1 and then 0, and that guy will say that, oh, it is balanced. No, no, it's not balanced. For it to be balanced, you can never see a negative number, meaning always you need to see same or more number of opening brackets before closing brackets or than closing brackets, because only then you can be sure that, oh, it is balanced, or we can add some closing brackets to balance it in future, right? This much check is sufficient because you have n plus m minus 1 as the string length, and at most difference could be n plus m minus 1. So just store the step. You define dp of I, j and k as at I and j whether or not I can get a difference of k. Your k can be anything from 0 to n plus m minus 1, right? So how will it work then? So you have dp of I, j and k is at I and j whether or not I am able to get a string which has a difference between the opening and closing brackets as k. And of course, you make sure that the difference is 0 to n plus n minus 1, not negative. Discard the negative completely, because if you have negative, you'll run into trouble. It's not a valid case, like I explained here. Lot of side cases, lot of chain of reasoning involved in the problem. That's what makes this problem a good problem. Now, this will be in case you have an opening bracket, let's say at I and j. What happens? So if you have opening bracket now, from where can you make a transition? If this is the opening bracket, you're like, and you want k as the current difference. So k is, let's say, some a minus b. But this a is after one opening bracket was added, right? But if this opening bracket was not added, if I want to look at a previous state, a would be 1 less, or it would be k minus 1. So the transition would be between dp of I minus 1 j k minus 1, or dp of I j minus 1 of k minus 1. I mean, if either of those was possible, so either add, let's say, one row before, like the top element, or the left side element, left is j minus, yeah. If either of them had a valid sequence with k minus 1 difference, then I or and j can have a difference of k, given that I and j have an opening bracket, because if there the difference was k minus 1, you incorporate this opening bracket, and now since one opening bracket has been incremented, your difference becomes k. I mean k minus 1 was there, so you add 1 on the, like a will be a plus plus. समझ जाओ, ठीक है. Similarly, if this was opening bracket, you know what to do. If it is opening bracket, the transition will be from k plus 1. Think about it yourself. I am not going to do it. And of course, k plus 1 for dp of I of j will be processed earlier, right? Because when you are at I minus 1 j, I mean cells which are previous to it, you will have processed all the possible states. So dp of I minus 1 j or ij minus 1 ka k plus 1 would also have been seen. Don't worry about it, because those are previous cells and all possible differences have been seen. Why k plus 1? Is because same thing, you have a closing bracket now. Hmm? If you have a closing bracket now, your difference currently is less. So previously it was more. And B is, so to speak, B is more now. B is more means K is less. Previously B was less, so it's K plus 1, transition from K plus 1. And that's exactly what I implemented here. So if you look at DP transitions, if you look at DP transitions, this is what I'm doing. Yeah. If it is opening bracket, we have a negative. If we have otherwise, it's a positive, and you just do the transition a minus 1 or this whatever is was there. You just do transition and make sure that it's like whatever cell you are going, the difference has to be between 0 or m plus m minus 1. Do not take the negative because discard those. Initialization is important. You can't just initialize at n plus 1, m plus 1, because there could be cases wherein, let's say you have cells. So I'll go through that case as well. So let's say you have something like this and sorry, this and this. Let's say this is what you have. Here you will say that, you know what, for this one the only possible combination is 2, like difference can be 2 only. But if I initialize it something like pad it on the left, well, the left column and the topmost row, if I pad it with something like initialize it 1 or something, then I run into a problem, because this will basically say that, you know what, so the left column has been padded with the fact that even with k is equal to 0, like no, um, no what, like without, with zero difference, if let's say something has been initialized with a difference of 1 also it is possible, with a, actually it is not possible. So what I'm saying is, don't add spurious values on left and top row just like that. In fact, initialize wisely. So wise initialization is like just initialize the leftmost row and topmost, leftmost column and topmost row with the real values. That's what I'm doing. So I mean, you iterate over all the values on the topmost row and just update that with whatever value is there. Of course, this difference has to be positive, because if it's negative, it's not possible. If it's negative, you break also, because after that it cannot be balanced in the topmost row. Similarly, on the leftmost column, I will move j is always 0. So if it is greater than or equal to 0, you will keep on updating. That's the only choice. This is what I'm talking about. So this is the only choice. So this row has only a single choice, and this particular bracket also has a single choice, which is 2. You cannot just pad something from before and say that, hey, with 0 difference we have 1 and with 1 difference also we have 1. That's not possible. Only possibility is 2 here. So you do it. Otherwise, if it is imbalanced, just break, because you can never get a balanced thing. So those are some side cases. I mean, I know there are a lot of side cases. First, you have to understand that balanced parenthesis check means it's sufficient to check that this difference is enough. Then you have to check how to wisely do that. Even if the moment you encounter something negative, you break, that's one thing. Then defining the states of the DP is also important. Then once you define the state of DP, like how to do a transition, that is important. And finally, also initializations are important. So there are 4 steps basically. You get the idea of a DP. You realize that it's exponential. So second idea is this idea. Third idea would be the transition idea. Fourth would be the initialization idea. So lots of ideas involved. That's what makes this problem hard. Space complexity would be big of n into m plus m minus 1. So it's big of n cube, so to speak, to store the DP array. And similarly, time complexity is also big of n cube as well. That would be this problem. A good problem, a hard problem, and a good problem. So the whole purpose was that even if I solved two problems. So this solution I knew before, but I had to implement today, and I ran into a few issues while implementing. But even if I knew the solution before, I had to implement it correctly, do the implementation correctly, go through the code thoroughly, make sure that I'm optimal with my time complexities and space complexities, and I'm using as less code as possible. I'm initializing correctly and all of that. And of course, the first question like you went through, there are multiple approaches, multiple ways to do the problem. So it's important to do this analysis. Also, I feel code is important, and only with this analysis, when this analysis is done, can we say that, oh, we did something. Anyways, I'll come to this next problem. This is also a tough problem. Maybe you can take a look at that, or I can go to explore, or maybe I'll go to problems. And I was solving October problems, and in October I don't remember from which problem I stopped solving. So I think minimum total distance traveled. Have I solved this? Minimum total, yeah, this is, I have solved. Minimum number of removes to make. This is a tough problem. I have solved this. Maximum number of moves in a grid, also solved. DB problem. Longest square streak in an array. I think I have solved this also. Um minimum of this, that. Number of smallest occupied chair, divide players, rank transform, check pairs, divide by array. Count square submit. Count square submitters I have done. Longest square streak I haven't done. This one I have done. This one I haven't done. So maybe I'll take this question first and this question second. I'll get some tea for myself and I'll continue. Does my hair look funny or something? I don't know how I look like. Hmm, it's looking funny. I'll take a look at the problem and then I have some cloths which are washed up. I'll have to put them to dry. Bachelor problems. Let's give a reading to the problem and then both the problems will give a reading while I enjoy my tea and we'll go there. Okay? Okay? Sure. This is something like longest common subsequence kind of problem. LIS, longest increasing subsequence. LCS is that DP problem, state transitions. How you came from, you store that and then you trace back. Or else it's just m minus 1, m minus 1. There is no replacement, just insertions or deletions. So this, and then you trace back. So length of the subsequence is at least 2 and each element is the square of the previous number. Return the length of the longest square street. Return minus another way. So this 3 because 2, 4 and 16 are present. What? Sorry? Oh, sorting. Acha, एक subsequence like a sort कर दो. So first of all, we'll just sort it. We'll sort it. Because that makes the problem much easier. If there are a bunch of ones also, it works. Otherwise, you'll have to start with a base number and then keep on searching maybe. Constants. Ah, stop there. First of all, isn't this just implementation? I think some implementation would work because the first thing you do, you start it, you check how many ones are there. That is one of the possible answers. Next thing you do, next thing you do, because if you take one, you have to always go with one. Next thing you do, you take the smallest number other than one, then you check its square if it is present or not. And if that number, the smaller number is seen, you don't process it twice because once you have processed means that is the long length you will get. And you move it, keep on moving the, jumping the sea ship, so to speak. It will not, it will be linear because you're effectively just moving through the entire, and this is implementation. So for 2 you will never get a 4, for 3 you will never get a 5, 9, so on and so forth. For anything, if you get something, you initialize your answer and you keep on moving. If your answer is 1 or less, you return. That's it. Hmm? I think this is implementation. for now. How to optimize it, how to store it, and see, the beautiful fact is all these numbers are in range actually, 10 to the power 5. So you just pick the largest number, then you can actually store the indices of these numbers. Indices नहीं है मतलब if it is present or not, something like that, right? Iterate over them and mark that it is there or it is not there. That's it. Or even simpler, use a hash mark. You don't even have to like, create additional space. I think hash mark for numbers is enough. It should be very optimal, right? This will be a tough question, likelihood. I mean, I'm just assuming that that medium problem is easy, but I'm still not sure. Could be that I've just interpreted it wrong. There could be some edge cases, as it happens with a lot of questions. This we know. This we know. This was a tough problem. Tough problem. This we know. These are the kind of problems that I actually want to do. This problem is very good problem. Like looks like a very weirdish problem. Hmm. Sure, sure. So let's say there are six nodes numbered 0 to 5, and we have edges for all these nodes, and whatever edges and weights we have, they have provided to us. There are two source nodes, one destination node, and the point is, what are you supposed to find? Return the minimum weight of a subgraph such that it's possible to. Okay. So this is the subgraph they're talking about. You just take these many elements. If you are interested in 0, 1, okay. This is the subgraph that they're interested in. Because from 0, you can reach 5. You can't reach 5 from 1 as well. And oh, wow. Isn't this a very tough problem? Hmm. Of course, there are a number of nodes. Edges is also large. That's a different story, right? So E log V is good only when you have a sparse kind of a matrix. Because if you have n square, it can be a dense matrix. It will be something like n square times of log. That's not what you want. Instead, if it is that, you will just do edge relaxation, kind of a extra. So remember, forward version is split and for all. Bellman Ford is single source, but it processes the edges. Process the edges. Right? If you and you process the edges for n minus one times, nth time if you have to process and something is happening, it's a negative cycle. Then you move back n times. Move n times, you'll reach one of the nodes and then just do a cycle. There was another thing. Yeah, normal Dijkstra is like you do n passes. In every pass, so one is processing of edges, one is processing of nodes. So in each pass, you find the closest one and then you process them. That's it. It's a relaxation. It's tough to do that. Maybe we'll just implement them one more time sometime. But yeah, this looks like a very promising problem. I'll start with implementing this one and we'll come back to this problem. Let me just put my clothes to try. Bachelor problem, guys. I'm a bachelor. I'm 24 plus. I'm living in Hyderabad currently, working for service now. I don't have any issues at ServiceNow. It's a great company, but it's Google, so opportunity of a lifetime. So I'm preparing for it. Still putting my clothes to dry. Yeah, I'm finally back. It's okay. Yeah, this was the question, right? We can just go ahead and implement this. So, I think one of the things we can do is to begin with just sort, begin, and so the first thing that I do. Next thing that I would sort of do is, I mean, you can see the number of individual values are itself in linear range, so you can just create an array and store them. But I don't think that is required. These are numbers. Hash map should be sufficient. So I'm going to just create an unordered map, something like this. Then also you can do something like, because ones will themselves form a streak. Next thing that we could do is this could be zero actually. So before returning, you do one thing. If it is greater than equal to 2, you return answer or you return -1. Right. Now here is where you have to do the jazz. So and do something like, let's say, you can define something like a chase x, right? And also maintain something like don't process the ones is what I'm trying to say. What's the use of processed? So once we will not see, and oh, okay. So if some square number is being encountered, you have to make sure that it is processed. Hmm. First of all, it has to be bigger than prev. It cannot be same as prev because you would have processed it. And even if it is bigger, if it is not processed, right? You haven't processed it. So currently this is this, and you have also processed it. You don't have to send it to a function, right? You can define get streak. Do one thing. There could be overflows actually. So you do one thing. Um, you store LLs, right? So everything you do, you store LLs, right? You are passing also. You pass LL. That will make it a bit easier actually. Here, what you can do is actually you don't have to do a function call. To be honest, why do you need a function call by the way? Yeah, I think this will be fine. This should be enough. Is it failing? I think it's in 64 underscore t. This function definition is also a problem. You don't require a function. I mean, why define a function? This you define as something like Linux is also I maybe this should be fine. So I'll tell you what I'm doing. So first we will sort it, and the first scene is like whether or not at all some number is present or not. So then we can track. We can just move through it. Now processed will ensure that we will not move the numbers repeatedly. So for example, let's say 2 is there. You move from 2 to 4 to 16, let's say 256. Later, when you see 4, you know that it has been processed. And if it has been processed, either it was processed by a like 4 itself was processed. By the way, if 4 itself was processed, we will not be processing it because prep will be same as 4. But if it has been processed, a longer sequence has already been found. So don't process it, right? So that's what will ensure that we are still iterating over all the elements only once, right? So yeah, I mean, it's just twice to be honest. So for every element, we can at most iterate through its chain. So distinct chains will be there, and one is the additional iteration. It's like n plus n. So first of all, for whatever numbers you have, if the number is x, you increase the count. Is one, you increase the count, and of course you mark that this is present. And answer can be count because if you only have ones, ones can also form a valid thing. Initialize answer with that answer could be zero also. Then what you could do is you iterate over all the numbers, and the number that you are seeing should be bigger than the previous value. The reason is you have sorted it. If it is not bigger, it is barabar. If it is barabar, it has already been processed. No need to repeat process. And it's the same chain. If it's present, it's present. If it's not, it's not. So it has to be more than the previous one so that there is no repetition of numbers as such. And if it is different, it shouldn't be processed. Processed meaning that previously किसी chain का हिस्सा हो. We are exhaustively computing everything, right? Because so do you even need to count one again then? ठीक है. I mean, I don't see a reason why we need to account for these ones. Do we really need to account for one? What is the range of the numbers? Oh, it's more than 200, so I don't think we can just do this. It's important to go through the constructs of the problem as well. You don't do this. Not required. You can't have all ones. Simple as that. So you remove it. So in this case, you will define prep as one which makes sense. I mean, whatever number you have, it will be bigger than prep to begin with, and it won't be processed. So it has to be bigger than the previous one so that you avoid repeated computations, and even if it is bigger, it shouldn't be processed again to avoid repeated chains. You set that to the previous value, you mark that it has been processed, and then as long as you have seen it, you keep on increasing the chain size. Yeah, and one more thing optimization you could do is you define a current as zero here, and the moment you see this, I mean everything's fine, you set current to zero and you increment current in local scope and you update your answer as well. Right? Yeah, that could also be a good idea. And this would still work. Right? You can sum it, see what happens. Yeah. So sometimes problems are just for implementation. Unordered map would work here. It's just iteration. We go n, but there is a log in complexity here due to sorting. Now the question would be, can we do it without sorting? So maybe what is the additional space used here? It's same as the order of the number of elements. So big O of n is the space complexity. So for this solution, space complexity is big O of n. It's not big O of max of whatever nums of I. It's just big O of n because you are just creating two unordered maps to store whether or not the elements have been processed. And time complexity is actually n log n. The reason being you are doing sorting. It's I think optimal sort is not merge sort. It's a combination of quick sort and heap sort as far as I remember. Right. So this is the time complexity for now, but I think this the whole point of the problem is someone will come up with a follow-up that how do you optimize this? So let's say we compromise on space. Could you maybe optimize this before more? Right. I think we can optimize. We don't really have to sort, maybe, or do we? The sorting will simplify the matters. Um, we don't really need to sort if we just use additional space. But for that, what you need to do is you need to iterate on the elements from smallest to largest so that you can process the chains. Until unless you sort, you cannot do that, but you can do if you just iterate through all elements that are present to you. You will compromise with space. So look at the submission. This is the submission, right? Space complexity is still beating. Why? If I again submit it, space should actually beat a lot. Is it still that? It's still that. I mean, I think space complexity should beat a lot of people. Why is it not beating? Can we optimize it? So current is this. What all things am I seeing? Sorting is it's sorting using of some space or something. But one linear solution which is possible is that you store a max value. Whatever is the max value is, you define a vector, right? So you mark that as one. Processed will be two. Hmm? Okay, and then you do the iteration over those numbers. So this is n log n because n is the total number of elements you have in the array. That can also be tilted to the power 5. That's a different matter. But there, for sure, it will be 10 to the power 5. Is the problem. If you look at solutions, bits and instead of 100 versus counting sort. Acha. Hmm. So some optimizations are possible actually. Yeah, of course, optimizations would be possible. So one optimization that I'm thinking of is compromise on space. Space that is create a vector of size max of all elements plus one and use one as present and two as processed. So what we'll do is we just literally just iterate over from 2 to the max length, and if it is 1 then you go through the chain, right? So um, I mean this is present and it has not been processed, so to speak. uh, uh, of course, because even if a number is present twice it doesn't matter. The reason being that uh, if it is present just once also, that's enough. You are just processing all unique elements anyway, so there is no repeat strings as such. Um, and just make sure that whenever you change the same array so that when it is two you don't repeat process. That could be a solution. If I just try to implement that quickly, what I could do is this. These are unprocessed. State of x is 1. The reason being that you are just seeing it for the first time. So you start processing and you will have to do the iteration here actually. It has to be 1 exactly. The reason being if it is 0 it means it's not present. If it is 1 it's present but not processed. If it's 2 it's processed. So if state of I is 1, then we define some I don't know, some 0 and sorry, you define int as 0 and ll also as 0. So here you will have to do all this shit, right? Yeah, I think this you can do it here. Now, process is not required. I don't think so. So I think this X that you're processing here is also screwing things up. You could do something like val is I and while scene of val into is equal to val. That's it. And you also set current to zero. You do current plus plus and you optimize your answer. That's it. I think this is enough. Yeah, I don't think anything else is required. I think this is enough. So you found out the maximum element. You created a vector to the state. So state is one, I mean it's present. And if state is one, you first of all update its state to 2 because you don't want repeated processings. So state is 2 or you can set to 0 also. That's also fine. I mean, one is the only case. It's present and it's unprocessed. Right. So and then the current value is this. You set the value here and while it is seen, you just keep on increasing your chain and since it is a L, it should be fine. While seeing, this is not correct. It's just it should be something like while state of val um, equals to 1. Can't be 2, not persisting. In that case also val into is equal to val and conversions. I think this should work. Is the LL error wrong answer? Why? Yeah, yeah, you'll have to sort it actually. So if you don't sort it, the problem is you see your 4. You will not see a 4, no? That's the problem. You are iterating from small to large anyways. Why? How? Why will you see a 4? Huh? You won't see it, right? 4, 416. You won't see it. That's the whole thing, whole idea. Okay, this you can't really do. You better you set it as not equal to 0. It's just mark process. It's not a big thing. What happened? Yeah, you will have to do something like mm, in that case, yeah, it will still have to be a long log. Otherwise, multiplication के time पे check करना होगा. It's a painful. See, see, yeah, that's what I was talking about, right? So there are other solutions as well, but I think what is it doing bit set? Alright, bit set as in bit set is that thing only, right? So for every element you just choose it. Got it. So this guy has done a lot of things because so in for two, the streak could be five because one, so this is two, three, four, and five. After five, it is not possible at all. Right? Yeah, it won't be possible. It's more than 10 to the power 5 as it is. Um, how is it more than 10 to the 5? This is a 65,000. It's not more than 1 lakh. Right? Is it 10 to the third 10,000? No, this is wrong actually. But still, per bond is still okay. Time complexity is this. Big O of n. Space complexity is big O of capital N. The reason being you are storing, and this is n plus n. Um, yeah, because this is the iteration on n, and this is iteration on capital N. I mean, people give a lot of names to this. A lot of names. See, this is the same code. See, dude is doing the same thing. Same thing. बोल रहा था ना. Dude is doing the same thing. ठीक है. The some optimizations is asking. He's doing something. He's doing. Uh, yeah. So this is he's using scene dot tie. To do this nonsense, you will of course get better things, a better time complexity. I know that scene dot tie null. So something to do with how it's processed internally within the compiler. But yeah, this is the idea. It's just implementation. Uh, Implementation efficiency could be what I can tag this problem as. I'll update my sheet. My sheet is open in the other laptop. I hope it's not visible here. I don't want it to be visible as of yet. So bitset is just a fancy name. So mm, what are bitsets? So um, fundamentally speaking, bitsets are really powerful tools. So they effectively will store numbers based on bit pairs. So in a sense of speaking, he is right because in your array, even if we have small n number of elements, we are capturing the largest value possible, and you are creating like a map which consists of zeros and ones, denoting whether or not the thing is present or not. So it's bit set in that sense. Baki implementation and the idea is same, and this is actually very interesting. So from an interview point of view, this is really beautiful. So this is something new you get to learn. That's why it's always a good idea to look at how people are solving the questions also. Anyways, the name of the question is longest square streak in an array. I just add this longest. What happened? Where am I typing? Longest. Yeah. Longest square streak in an array. This is implementation problem. It's a medium level of problem. I just do this so that I don't have to do the hard work. It's an implementation problem. And just going back to solution of that guy, so everything else is fairly simple to understand. So this is like, yeah, compromise space, that is create a vector of size this and use one as present and two as processed, something like that. And after implementing that, you will have space complexity as big O of n, where n is max of all elements in null's array. And of course, your time complexity is big O of, first of all, it's small just to iterate to find the max, and big O of n for the processing next. So you iterate over everything. If it is 1, it means it's present and not processed, so then only you just move ahead. You can mark it 0 as well, but that's just going to create some issues, implementation issues, but rest of things are very simple. Where N is number of elements in array, and N is small is the number of elements in array, N is maximum. For some reason, I just remembered the trip back from Araku to Vizag. Beautiful trip. Also, the trip from Raukela to Raukela. When we reached Raukela, mountains everywhere. Beautiful trips. So this year has been filled with a lot of trips. So, I've been quite. I'm blessed to be working at such an organization. To be honest. Anyways, these are the time and space complexity. So this is the original time and space complexities, and it's actually quite cumbersome. And this could actually have been optimized. I was actually using a space repeatedly. That was the problem there. So we look at this submission, it's actually beating everything. See, it's like, I mean, beating everything quite a lot. The reason is use of repeat variables, something to learn. So declare global variables and use them repeatedly. Why do you want to declare variables within a loop, right? And yeah, that would be the idea. So you can give it fancy names like bit sets and all, but the underlying idea is the same, right? So you don't have to spend time in sorting. You just create a global array and process it. And this is actually very interesting, that the highest streak could be 5, because even if the smallest number is 2, if you keep on squaring it, you can square it. So square it once, twice, thrice, 4 times, right? So if x is 3, 3 to the power 8 is this. So 3, 3 square, 4, 8. Even in how many operations? So 1 operation, 2 operations, 3 operations. And 3 operations, it's already like huge. Right? Similarly, it's 5, then it's again the same thing, right? So 5, 5 ka square is ka square. It blows up. Right. Streak is how many numbers are. So if, let's say there is something like 20. 20 ka square is 400. 400 ka square is 16 into 10 to the power 4, which is again big. So that's what he's saying, that you can actually be very wise and just trace your numbers between, let's say, 2 to 20, and then for each of these you process whether or not it will be present it's present or not. Just you just process those many numbers. So you have 20 numbers, right? um, but that's the thing, right? So if you have a streak of 2, actually you can do it till 100, I guess. 100 or 200, 300, 400, maybe 1 till 400, because 400 ka square is beating 10 to the power 5. So it can't be more than that, because sequence lengths have to be at least 2. So maybe you iterate from 1 till 400 and you do this. That could be also a good one, whether or not it's present. Just move on cycles. Right. That could also be a way. Yeah, this is like early stopping. It's very good solution. It's very good solution. It's very good solution. No need to like overanalyze. So you got a brute force solution, then you optimized the time complexity, right? You don't have to do a sorting and stuff. And then you also made an observation that, you know what? Even if you consider the smallest element, at most you can do a streak of 5, right? And then you can just search for maybe elements of 1 to 100, 400 or something, and try to find a streak, right? And each streak can have like 5 elements. So it's like 400. into 5. It's too small. It's for each element you are just iterating 5 times. It's like what? 2000. Oh, it's extraordinarily fast. Hmm? Right? If it is present, you just do that, right? Why do I have to iterate over all the elements? Hmm? And then go through the painful process again and again. So, anyways, if you are moving from 2, the streak point will be till 5. That is for sure. So, that you don't have to worry. Hmm. It will never be present. So, that is still 5. But still, number of elements is very large. Right? But then again, you can't really process for all different elements. So, and for elements which are above 400, anyways, you will just process it once and then like maybe it's not present. I mean, ultimately, complexity is that only. So even if you like iterate from 1 to 400 and do the thing, it will be like 400 into 5. Ultimately, it's that only because even if you are doing this code, writing this code, the only suboptimal thing is like let's say one of the numbers is very large, let's say 1000. So you are iterating till 1000, but for each of them, at most you will go to 5 times. That is fixed. While loop maybe you will go at least 5 times. Then again, you are not really going into 5 times for each of them. You can go 5 times for numbers which are less than or equal to 400. So it will be 400 into 5 at most 2000 plus some additional movements that you can do. So that is the only thing. I mean, yeah, rest of the things are like so movements of 5 is only possible for this many numbers. In fact, a movement of 2 is possible for this many numbers. Rest of the numbers are just singular. So anyways, so that would be the idea. Yeah, not spending more time on this. Moving on. Implementation problem. I think if I just explain this much, it's good enough for from an interview perspective. How much time has been spent in this? 1.5 hours. Okay. So mental analysis of a problem, of couple of problems. So one problem solution I saw today, the other solution I knew beforehand, but still implementation was painful. I mean, state transitions are always initializations and state transitions are always important things in DP. So that's something to look out for. Implementation is important. Implementation is always important, regardless of what you say or what you do. Implementations matter. Now let's come to this problem. This was actually a tough problem. I mean, so the number of nodes and the number of edges you have are all in linear range, and you are supposed to be doing something which actually looks quite tough to begin with. What you are supposed to do is you have two sources and one destination. You are supposed to, you know what, pairwise distinct just means that everything is different. A, B, C, A is not equal to B. A is not equal to C, P is not equal to C. It just means that nothing is equal barabar each other. Assign anyone is barabar each other and it will break. That's it. Okay. By the way, I don't think any math, any explanation was required on this. Right. Yeah, I don't think any explanation is required on doc for that particular problem. The best you can do is iterate from 1 to 400 and 2000 is the most that you're going to get. Here also same thing will happen because 2 or more times or even 5 times movement will happen from 1 till 400. So that is preserved, but the only thing is you are additionally moving across till the maximum number, which is still, I mean, within time loop. So that's all right actually. It's okay. We know the optimization. I mean, it's all right. It'll always work. It'll always work. 1 till 400, 2 till 400 maybe, and just do your nonsense. Because even if your number is present more than 400, if you square it up, it's itself beating the highest number that is present. So, of course, you will never be able to do that. But that's not a generic solution, to speak. Generic solution is sort it and process it. Observing that the highest value is small, use this. And once you observe that, you can actually make some more observations as well, like that guy did actually. Anyways, coming to the current problem. Okay, we need to find a subgraph which such that from both sources you can reach the destination, and the sum of the weights is as less as possible. If it's not possible, it will minus one. Correct. Mhm. What do you do? Can we do a extra? What if I run a extra? I can run Dijkstra, right? Because if I run Dijkstra from 0 to 5, the answer is 6. Hmm. Need to do as common as possible. So I'll have to write a few things. So maybe I'll have to think about this on board. This is minimum weighted subgraph with the required paths. Here, so you have SRC1 and you have SRC2. So you have source 1, you have source 2, and you have a destination. Now, what could be possibilities is you could just consider distance of SRC1 to destination. I mean distinct. Let's say they are different paths. So you consider this as a set, you consider that as a set, and you add them, right? So it could be something like this plus distance of SRC of 2 to destination, assuming that we are running the extra differently. Or let's say, so what are the possibilities? You have a destination, you have two sources. Either you reach through different paths, or if there is a common path, could be that you start from 2, go to 1, then go to this particular position, or you start from 1, you go to 2, that is better, then you reach the destination, or you could have a common path. Oh, that is tricky actually. This is least common ancestor, is it? This is actually tricky. So this you do, this is completely distinct. Distinct. Or you can have distance of SRC1 till SRC2 plus distance of SRC2 to destination. Um, this is SRC1 to you go to SRC2, you go to destination. This is one more path. Or it could be something like SRC2 say we come till SRC1. Then we'll go from SRC1 to destination. I do expect to be asked to implement some strong algorithms, Kosaraju's algorithm or Darjan's algorithm, so to speak. Difficult algorithms could be asked to implement during the interviews. I just hope it's not in the second round. Second round, if second round goes well, then I'll have a ray of hope that yeah, you know what, there are just two more DSA rounds. We'll somehow go through them. So in this case, the path will look something like SRC2 till SRC1, and go to destination. This is one other choice. Or you could have you add the two paths. Let's say those are the three things. Like I'm not able to represent. So either it's completely distinct, you add this, or it goes through one or the other. So if it is not going through one or the other and it's not completely distinct, what are the possibilities then? या तो पूरा डिस्टिंक्ट है, या तो इसके थ्रू जा रहा है, या तो कहीं पे मीट कर रहा है, right? So it is something like distance of SRC1 till destination plus distance of SRC2 till destination minus distance of common node till destination, right Ji? I think these are the four possible cases. These are the only possible cases. Are you mark it something like this? Okay. All right. Only four things are possible. Only four things are possible. So how do you go about this? See, 2 and 3 are very easy. You run a Dijkstra from SRC1 to destination and SRC2 to destination, and you just add, right? If you just add, so could be that it's going through, but doesn't matter. You just add it, right? So let's say there is one path going here and then there. That is one possibility. Or maybe you go to this node, you come here and go there. In that case, you will again get optimal path because because see, if SRC1 should go to SRC2 and then there, right? Why will SRC2 to destination be anything else? You can blindly add. Yeah, you can blindly add. But if that is the case, then SRC2 से SRC1 plus SRC1 से destination can have overlaps. But then SRC1 से SRC2 and SRC2 से destination will be fine. So one of them will work, right? And even if you have distinct things, it's okay. But you need to find a common node. You find the common node. So in this case also you see this is a common node, right? I think one is a common node. Is it? 0 node? Yeah, one is a common node. So you add this entire path and you add the path from 1 to 5 and you subtract this path because this is the path of common node. How do you identify the common node? It's not like for every node you can find the path. No, you can do two DFS, two Dijkstras you can run. How many edges are there? Edges also can be large, right? Okay. It's a very dense graph. In square, log n is painful. E log n. Just go for n square, but here you can't go for n square. It's normal heap extra you will have to use. Normal ape extra, because that is just greedy, some sort of brute force or something. This is greedy actually. Dijkstra main ape is greedy. That is DP. Path relaxation is DP. Hmm. How to do this? I think I'll take a short break and I'll yeah. So I had to take a break, but I think I have kind of cracked this problem. Um. So first of all, we'll have to use LL here. It's the same thing. Let's go T. Now, what I thought was this thing. So we want minimum distances from all nodes to destination. That is a tough nut to crack. What if I find out distances from the destination node to all the nodes? That is just Dijkstra, right? And we can just do a min heap Dijkstra at that, which is simple. One would think that that is not possible because the edges are in a different direction, then that would give us the wrong values. Reverse the edges, right? So, for example, here 0, 1, this path is there. If you reverse the edges from 5, you will be able to find the distance, right? So, uh, if you reverse the edges, the closest distance from 5 to 0 is same as the shortest distance from 0 to 5 in the original graph. So, for example, if I reverse all edges, note that reversing all edges is important. If I reverse all edges, let's say there is some more optimal path from 5 till 0. If that is the case, on in the original graph also from 0 to 5, there is some other optimal path. So reverse the edges, right? Like process the edges in a different fashion, right? And um, yeah, so you have this. What is the individual values? So n is this much, edges is this much, edge of eye length is this much, and weight is also in range. Um, these are all in n minus 1, which is fine. So you can create an adjacency list, and yeah, you have to create a full adjacency list. You can't just go through edges. You can process edges in Belgium for not here. You have to create an adjacency list. Everything is from 0 to n minus 1. That is the most important thing, I think. Um, yeah, that is a beautiful part. And the interesting thing is that 10 to the power 5, so it can be LL. That's why they have given LL. Full graph. Uh, the interesting part here is that I'll tell you. I'll tell the most important interesting part. The interesting part is that uh, once you have processed it, so effectively you will have shortest distance for, you can create a vector called shortest distance for all nodes. So it's like from this node, what is the shortest distance to the destination? Then it is very easy to get your job done because you can just assume every node as the pivot node. So for example, if I assume some node X as a pivot node, let's say X is my pivot, right? So this was this case, right? Common node in path. If this is my pivot node, I'll do a distance of source 1 to X, shortest distance, plus source, sorry. So no, I don't think this is how we'll have to proceed. If this is my pivot, like this is how we're proceeding. So it will be something like X to destination. Like it will be something like distance of X plus, I mean everything is to destination, so you don't have to worry. So yeah, this is important. The reason is you don't have distance from SRC to X, right? You only have distance to destinations. So it's distance to X, distance of X. Hmm? Hmm. Just a second. You have to take yet another break, but as I was saying, So what you could do is, for every node, assume this is the pivot, then you have distance of x plus, can't just assume that as the pivot, right? Because if you have distance of source, hmm, how do you know when it is crisscrossing? So you know distances of every node to the destination, but you still don't know. You still don't know distance of. Oh yeah, you run. Yeah, yeah, sure. You run three extras will be required. Yes, you run three extras. So the extra one, uh, distances from each node till west. The extra two, distances from SRC1 till each node. The extra three, spelling गलत कर दिया क्या? Okay. The extra three is distances from. Is it even recording? I want this record. This is a good problem. I think it's a really good problem. Yeah, distances from I think SRC2 till each node, and this is like shortest or test. You can say shortest distances. Shortest distances. So let's call this something like, let's say, dist of x, dist 1 of x. Let's call this, let's say, so let's say this is dist 2 of x, and let's call the third one, let's say, this 3 of x. Now assuming that you have x as a pivot, what you can do is, if you're considering this distance, you will just say, so it's dist 1 of x plus distance of source 1, so dist 2, uh, dist 1 of x is like distance from x till the destination, and dist 2 is have a, it has a different meaning. So dist 2 of something means what is the distance till this node from here, whereas dist 1 of something is what is the distance from this node to destination. So it is dist 2 of x plus dist 3 of x. I think if we assume everything as a pivot and do this, we will be done. Because assuming we actually have a pivot to go through, this is taken care of, this subgraph. What could be the other cases? So let's say, so this case is easily taken care of. This is done. And let's say we are just interested in joining them, right? So it is like dist one of source one and plus dist one of source two without any pivot. That case, I think you will have to take it separately. So this is with everything as a pivot, or you can do dist two of dist 2 of x plus, no, it is dist 1 of x plus src1, so dist 1 of src1 plus dist 1 of src2. This is like dist 1 is the distance from here to here, so you directly add it, or you take distance from x and uh, to this, but you add these two distances or these two distances, or it could be that either it is completely distinct or it joins at some point, or it is intermediate in itself. In that case, it should be this distance. Acha. Self distances can also be computed. So shortest distance from source 1 2 itself should be 0. So that also makes sense. Yeah, I think uh, we are through. This is it. Run three extras, right? I think that is the solution for this problem. So um, you will run the extra one to store. uh, yeah, you will actually have to create two adjacency lists. Mhm. So the extra one to store min distances from each node till destination, then run the extra two and three using a common method to store distances from SRC1 and SRC2 till each node. Store min distances. Correct. So here you will have to create a density. So vector of um, integers integer list arrived. This is the first one, and it will have some n minus 1 elements if I'm not wrong. We'll just reverse it. So for vector, yeah, and the problem is you will actually have to store. So for every element you are storing adjacency list, you store a pair of elements, right? So you store pair. I think yeah, that would be better. So for vector int v in your edges, so from to 2 you just reverse it. So adjacency list of v of 1 dot push back make pair v of 0 and v of 2, right? This is how you process it. Ulta kar diya basically. Right, because it's from here to here but you're doing it in reverse fashion, right? um so we'll have something like vector ll dist1, which is like n minus 1, right? And what we'll do is, you can you do something like build extra build extra on your destination. From destination you want to process your adj list live, right? And you want to optimize this one, okay? And here all you really need to do is you will define vector parent teacher list n minus 1. So you can define this here. Actually you don't have to do this shit, you just define it here. And here all you need to do is you can just push back control C control V, you push back the normal form v of 1 and v of 2. This makes sense. And you'll have three distances basically. So you'll have, you create a couple more, sorry, dist 2 whose size is n minus 1, and dist 3 whose size is also n. Note that the definitions are a bit different. So dist 1 is right, dist 1 of something is the minimum distances from that node till destination, whereas dist 2 of something is like, um, dist 2 of something is what is the minimum distance to this node from source node, and this the other one is for source 2. So build extra with destination as starting point and adjacency list reverse and everything, You know that because from destination you will start. So effectively you are storing distance from destination to distance, but since it is ulta adjacency list, it's storing this. So again you do a build Dijkstra from source 1 with ATG list and optimize list 2, and you build Dijkstra from src2 till ATG list, process ATG list, and you use this trick. Now optimize the answer. How to optimize is um, so let's say LL answer is something like you know what, the first is like uh, yeah, the first answer is like dist1 of src1 um, plus dist1 of src2. I mean it just distance from destination to sources, but we have reversed everything, so it's just minimum destination condition. This is the initial answer. Then you can define your pivot. So for I equal to 0, I less than 10, I plus plus. Answer is minimum of answer or dist1 of I plus dist2. So dist1 of I is from I is the destination. Dist2 is like from source 1 say I plus dist3 of I. I think this is enough. Then you just return the answer. We will return the answer. Dinner time is also very close by, so I just want to finish this as quickly as possible and be done with this. All that I need to do is define the function build Dijkstra. What I need to do in Dijkstra is in source vector we will type first, don't worry. So for pair, for another vector, this is addition list, and we have vector list. Right. All you need to do is first is the distance of source is 0. Then what I need you to do is priority queue. Do you really need to create 3 priority queues for the calls? Why can't you just clear it? So some optimization is possible. That's what I'm trying to do. You create a priority queue here. Priority queue. This priority queue will basically have the minimum distance. It will have pair of LL int, vector of pair of LL int, and greater pair of LL PQ. You pass this PQ. Pass this signature into the function as a reference, right? What you can do is you do a pq.clear, right? And all you need to do is while not pq.empty. Of course, one thing that you need to do, you need to initialize all of this to some very large values, for example 118 or something. The reason being that you know what, these weights are 10 to the power 5, and there can be these many edges in total, so it's more, I mean you're just maximizing. So something is infinity just means that it's not reachable, so to speak. let's keep it 1 is 16. Actually 1 is 16 is what we should keep. If one thing you can do, return answer is less than 1 ही हर एज का लेंथ इतना है, even if you include all edges and all, so it should be less than to 1 is 16. If it is less than that, return answer, else return ll minus 1. Yeah, I think that's good. All I need to do is yeah, pair ll int p pq dot top, and we have pq dot pop. So we'll just define distances now. ll curtist is p dot first, int what am I pushing, int element, or better you denote it as node, is p dot second. What you can do is distance of mm, mm, distance of node is current distance. You don't have to do this actually. All you need to do is you dot push make pair 0 and source. So like this is what we'll get at first. So distance of node is your source. Current distance is it just 0. That's it. The next thing that we do is if scene of node, yeah, of course you can encounter things. Continue. Scene of node is true. Then you do something like for index in adjacency list of this node, whatever adjacency list you are passing. If you have already seen it, what that means is that already there is an effective way to reach to that point. If not seen x, then people dot push make pair whatever is the current distance plus you will have to iterate over pair, right? Pair. You've seen x dot first, because while we are making the pairs, we are pushing the distance here. Yeah, if you have not seen it, you make a pair which is current distance first plus um, long of x dot second. So this is the distance, and you push x dot first because you have not seen it. If you have seen it, it is already processed optimally. But since you have not seen it, you push for this present node whatever is the current distance plus like it's present in its adjacent list, so whatever is the weight to reach that, you push it. Yeah, I think this is it. Return. One thing that you can do is that yeah, you'll have to pass a scene also. You pass scene everywhere. Scene, scene, scene. right? And one thing that you could do is, can you pass n actually? Why don't you pass n as well? Just pass n, just for verbosity, because you have to initialize it to false. Correct. So here you have a vector pool ampersand scene, this n, and you have to do something like scene of I false, right? Because you have n nodes, you are trying to build a diagram, so everything is unseen. You clear the priority queue as well, and you make a pair. Zero is like the starting distance, source is there, but it's not empty. You pull out element. Current distance is this, node is this. If you have seen the node, continue. If not seen, mark it true. Distance is this one, and you keep on pushing. So whatever is there in the distance is keep on pushing. And this is this because we have reversed the way you are processing the elements. This is adjacency least. That's it. Correct. Yeah. So effectively distance of one is distance from here to that, and this is actually distance to this, like from source to this, source to this, source to this. Right. So either you use a pivot or you use a direct distance. I think that should work. Let's see if it works. I'll lose. Maybe we'll just pop out all the elements in priority queue. What happened here? This is correct, right? Okay. You have to pass priority queue as well. Runtime error आ गया है for some reason. Why have you defined it as this? Shit. Should it be n? It should be n, right? This will also give you some error. This is also runtime error. Everything will give runtime error. For some reason, I have defined it as n minus 1. This will. This should be fine. Yeah. And fundamentally speaking, this should work. Let's see. Some runtime error is happening. Actually, a lot of test cases have passed. I think it will pass. But buffer flow, I mean, runtime issue is happening. How do we prevent this? Is actually you're adding the distances, right? All the distances are this. Hmm? You're starting with 0 and you're adding the distances, and you're optimizing the distances. Hmm. Even if you add 3 distances, it shouldn't overflow, right? Should it overflow? It shouldn't overflow. 1 is 16, 1 is 16, 1 is 16. क्या हो जाएगा? I don't think anything will happen. I don't think this is the issue. It's recording, right? It's already quite a long stream, to be honest, but still. I'll have dinner, but only after I submit this. Maybe I'll pause it and I'll come back for some explanations, or I'll explain it right off the bat because I'm quite hungry. So what we are doing is all the distances are initialized to infinity, and also the scene. How come it is this? I think that was the problem. The other thing will not be a problem. Let's try to solve it. I'm actually expecting an accepted answer here. Yeah, it got accepted. See, it's a hard problem, but it got accepted. Right. Maybe some optimizations could be possible or whatever, but the solution is complete. And the idea was very good. This occurred to me while I was on the cab. That's the joke. Let me paste it, and the solution is minimum weighted subgraph with the required paths. So this is minimum weighted subgraph with the required required paths. Is it? हम्म इसको थोड़ा extend करते हैं. This is a hard problem actually. um, it's not that easy. So I would say this is, I mean, Dijkstra and some implementation. Yeah, Dijkstra plus implementation. You need some a little bit of little observation actually. Some observation is required to solve this problem. It's not like a straightforward endeavor to solve this problem. I'll come to this analysis. So, are there some other solutions? Have I solved this before? First of all, no. Easy C++ three dimensional. See, seriously, we know. I know, and I thought of it myself. I know how to solve this. Three Dijkstras. Are you kidding me? I have done that. Three Dijkstras. See, Dijkstra 2 and 3. And I'm happy that I solved it without looking at the solution. So, yeah, congratulations to me. I'll pause this video now. I'll have dinner. I'll come back and do some analysis regarding why some overflow is not happening, why it is correct, or time and space complexity analysis, and all that. And we'll close this off. I've already added this problem, so that should be fine. But I'll still. The four questions are done. Count unguarded, longest square streak, and minimum weighted subgraph are the new problems. Um, two medium and one hard. And another hard problem I had already known, but implementation was quite difficult. So it's okay if you analyze all the problems correctly, properly, fully, and even if you solve four problems, two hard and two medium, I think it's a good day, right? You are being algorithmic, you are solving something, you are writing some code, so and you're explaining something. I think in the end of the day, that's what matters the most. Sure. So I did a lot of explanation here actually for this problem. So I'll pause it right now. I'll have dinner, and once I'm back, I'll give some more explanation, some more analysis or insights into the problem. Yeah, resuming the session, it's already been over 2 hours. I'll just quickly go over the time and space complexity analysis and the correctness analysis of this problem. So space complexity is very easy. So I'm using two adjacency lists, each having like we are storing for n nodes. We store all the elements which are adjacent to it, and at most we have I guess 10 to the power 5 edges. Is it right? Yeah, so we have n things, and if we just sum up all the things that are stored, it will be big of m. So that is one thing to note here, that although adjacency lists look like they are taking up space complexity of n, it's actually n things, but each of them will store some connections, right? So it will effectively turn out to be m connections that they store. So you can, in short, you can tell something like n plus m is the space complexity. My bad. So this is the space complexity here. Distance, it's just n. Priority queue will store distance of n nodes at max. Scene is n, right? So I think these are the things we are using. So two adjacency lists will be used. Scene variable will be used. Priority queue will be used. Distances will be used. So it's like 3 times n, 4 times n, 5 times of n, right? Because priority queue is seen 3 times of distance, and there are two adjacency list n m. So in short, if someone asks, the time space complexity to speak is of the order big O of n plus m, we can say. So it's 5 into n plus 2 into m to be specific, but the order is n plus m to uh, be asymptotic in nature. Time complexity is even more easy to compute. It's big O of max of n or m log n. Yeah, so m is like the number of edges. By the way, n is the number of nodes which has been given. Number of edges, let's say it's m. So in that case, space complexity is big O of n plus m, because we have we have 5 storage containers which have n elements each, and 2 with m elements each, m plus n elements to be specific. So order is this, and time complexity is big O of max of n or m log n. The reason being that we are iterating over edges, which is big O of m. We are iterating over what we are doing then is yeah. So once we have uh, these, we are iterating over edges, which is big O of m. Then we are creating distance matrices. So internally distance matrix creation is also big O of n, to be specific. And scene vector is created, all of that. Even if we ignore that, when you do build Dijkstra, so we have n vertices and m edges. So ultimately you're processing m edges, and for each edge you're creating a min heap of maximum n nodes. So it's m log n. E log is the complexity, because min heap Dijkstra is used here. We can't use path relocation Dijkstra either. For that, number of nodes can be something like 1000, and edges should be n into n minus 1. So in that case, if you do e log v, it is something like n square log n. So instead just use n square, that's it. So here build extra is m log n, m log n, m log n 3 times. So this is Dijkstra is m log n. Creation you can consider as big O of n time complexity, but to be specific, we're again doing an iteration for all nodes as pivots, so big O of n. So those two things are there. We will not consider big O of m, because m log n definitely has a bigger factor. So m log n or n, maximum of those will be the time complexity. To be honest, m log n will be the general time complexity. The rest of the things are fairly straightforward. So you have a adjacency list, you like you have a source node, you have adjacency lists, and you have a destination distance array. So from source to source will be 0, and for every node you are seeing from source, you have to just have to populate that, right? So ideally distance 1 of x is something like distance from destination to this, but since it is reversed, this is a reversed computation, it's same as from this to that, just to be sure, and this is this to that, for source and source 2, just to be clear on that. Okay, so Dijkstra is pretty standard. You pick this least element. If it is seen, you continue. If it is not seen, you mark it seen and assign the current distance, and then you push into main heap if something is not seen. It's pretty standard m log n, e log v solution, and everything else is fairly straightforward. So space complexity, time complexity is easy to note. That's easy to see, and this will never overflow. The reason being that so at max you can have 10 to the power 5 edges each with 10 to the power 5. So max value will be 10 to the power 10. I took 10 to the power 16 just to be safe, but even if we add everything, right? So 3 additions will be 3 to the power 16, which is still not overflowing. You can't take 10 to the power 18. Maybe like if you take LL max, 3 times LL max will overflow. That is another issue. This will not overflow, but that case won't be considered. Infinity won't be considered due to this. That's taken care of as well. Just a little bit on the idea. Think about it. You have two nodes, one destination. Either you connect it completely disjointly. Here is where I explain. You have two nodes, two sources, one destination. Either it's completely disjoint or it goes through someone. Think about it. There are only two ways. Either the paths are completely separate or they are common from one node. So if it's common from one node, iterate over all nodes, that is common. That distance plus these two distances to that node. And if it is even one of those nodes, it's fine, because the common distance will stay from one of those nodes to the destination. From the other node to this node, distance is added, and self distance is 0. So that works as well. So that effectively takes care of all the cases we have. And it's a quite neat solution to the problem. And if I see the solutions that people have submitted, almost everything is like extra, three extras. So yeah, I think it was a pretty good session, pretty effective session at that. Got to learn a lot of things. I'll maybe pull this sheet over here now. So here, this last four problems is what I did. This one I had tried solving from yesterday. I wasn't able to get the approach. Today I got it. Like the most optimal approach is not that easy to figure it out. So that would take some explanation. Basically, observations like these would be required to solve that particular problem. Then this one I already knew how to solve, but again, implementation is painful. You have to take care of side cases and all. Again, there is some thinking to be done in order to solve that problem. Then okay, so this is a purely implementation problem, no need to think about it. Although there are optimizations, so you do a brute force by sorting, otherwise you would use a bit set array like all the elements which are present and then use that, or you do some observations like at max. I mean, even if you do it once, you need a length of 2, you can go till 400. So for 400, and even 400 into 5 is not possible, so you'll have very few number of calls, and ultimately that's what will happen. But since if you're declaring all the elements, you'll have some additional iteration, but that's negligible. So that is another thing to do, and additional space will also be required, by the way. You don't even have to like store beyond 400, because there you won't even have two calls. So what's the point of doing that? So there you can save on space and time as well. But regardless, you're just using some linear space and linear time additionally on top of what you should be using. So that should be fine as well. That was fine. In fact, it was beating a lot of people. But such observations are good from the point of view of interviews. Final question is this one, the one I solved just now, minimum weighted subgraph. So only four questions this day, but still, if you solve a problem, you analyze it, you go through time and space complexity, you go through multiple approaches, right? So this has multiple approaches. First of all, whether or not to use an array, what if you don't use that, what will happen if you use that, and then couple of approaches. This has one bad approach and one optimal approach, and then correctly implementing that. This has multiple approaches and multiple optimizations which are possible, observations are possible with varying complexities. And this has a single approach, but it has some neat observations and neat implementations as well. So I would say it's all right. You solved a couple more questions in the evening. It was a productive day in the end. You solve, you discuss, you analyze the time and space complexity. You go through the approaches and you try to explain as much as possible on Google Doc. That's what is the ultimate thing to do. So I think it's a pretty good thing that happened today. So I think that's all from my side for today. I'll try to solve some more problems. I'll try to do as much as videos possible, as much as solving, discussion, and all before my second round, because once my second round is done, back to back rounds will be there for 3 and 4. I really hope I clear